All right, so we are moving from top to bottom in terms of network layers. So we started with application layer, transport layer, and so on. So now we are at the network layer. We are still using the slides from the book Computer Networking, a top-down approach. So the book actually divides this layer into 2 chapters, but we will be focusing this part because later on when we are going to talk about security, we need these topics. So I'm going to focus on these parts. So our goals are as follows: understand principles behind network layer services, focusing on data plane, network layer service models, forwarding versus routing, how a router works, addressing, generalized forwarding, internet architecture. So these are the things we are going to focus on. Instantiation, implementation in the internet, IP protocol, not middle boxes, and so on. So let's start with an overview where we actually, the book divides this layer into data plane and the control plane. Then we are going to talk about what is inside the router, input ports, switching, output ports, buffer management, scheduling. Then, more importantly, this is the part actually most students interested in, because in the security part, we need to, how IP protocol works, what is IP version 4 and version 6, and so on. So we will be talking about datagram format, addressing, network address translation, in other words, NAT, IP version 6. Then we are going to talk about generalized forwarding, software-defined networks, and here we will talk about open flow protocol. Then we will briefly mention middle boxes. So let's look at network layer services and protocols. So as I mentioned, we started from the top, talk about application layer, transport layer. Now we are at the network layer. So the transport segment from sending to receiving host. Sender encapsulates segments into datagrams, passes to link layer, right? So receiver delivers segments to transport layer protocol. So we already talked about encapsulation, so we know the idea. Here the trick is that we have many routers between these edge devices. And these devices, these routers, actually don't care about transport and application layer. This is why they live in the network layer. And also some switches only work on link layer, not in the network layer. So this is why it was a good idea to, divide the whole network into layers. So this way we can actually construct internet like this. Network layer protocols in every internet device, host routers. Routers examines header fields in all IP datagrams passing through it, moves datagrams from input ports to output ports to transfer datagrams along end-to-end paths. The actual router knows which router to send, right? Because they actually know the topology somehow. And these are actually stored in their tables. And depending on the IP, they know which output port they are going to use. So this is the thing that we are going to talk about. So there are 2 key network layer functions. One of them is forwarding. Move packets from a router's input link to appropriate router output link. Routing, determine route taken by packets from source to destination. So here we need some routing algorithm. So if you want to see the difference, in the forwarding, it actually happens inside the router. So it takes the input and knows which output port to use. But for routing, we actually need to know this paths so that it can send it there, right? Sometimes people use these 2 words interchangeably, but of course, they are not the same. So again, our books like analogies. So this is like taking a trip. Forwarding, process of getting through a single interchange. Routing, process of planning trip from source to destination. So that is the main idea. All right, data plane. As I mentioned, the book actually divides this layer into data plane and control plane. At the data plane, we are actually looking at the router locally. So per router function, it is local, determines how datagram arriving on router input port is forwarded to router output port. Okay, here this process actually happens by router looking at the headers and then doing its job. But most importantly, it has to be fast. This is the main thing here. Okay, it has to be in maybe microseconds or less than milliseconds, maybe, because we need speed here, right? So this is why generally we don't do it in software, but do it in the hardware level. Okay. So actually, we will talk more about in the following slides. Control plane network-wide logic determines how datagram is routed among routers along end-to-end path from source host to destination host, right? So here we need routers to exchange information somehow so that they know where the edge hosts are, so that they can, construct a path. Two control plane approaches, traditional routing algorithms implemented in routers, are more popular these days. Software-defined networking implemented in remote servers. Okay. Let's look at per router control plane. Individual routing algorithm components in each and every router interact in the control plane. Okay. So all of them has some information exchange using the routing algorithm as shown in here. So they know which output ports they are going to use depending on the input headers. And the book device is as follows. Control plane is the exchange of the algorithm for the routing. And this part actually locally happens. Looking at data arrives in input ports. Looking at the headers, router locally determines which output port it should follow. This is the main idea behind dividing these two layers. Software-defined networks at the control plane works like this. Remote controller computes, installs forwarding tables in routers. So IDs as follows. We have some maybe cloud services and so on. They are remote controlled and they send you the routes. So this way, you create these tables according to information you receive from there. So question is, what service model for channel transporting datagrams from sender to receiver? Example services for individual datagrams, guaranteed delivery with less than 40 millisecond delay. So in order to do that, you have to, transport data at the router at the hardware level. This is what I was trying to tell you. So deciding which port to use should be really fast. And we also mentioned that there's also queuing at the routers, and you can lose data at the routers if you have, buffer overflow and so on. Example services for a flow of datagrams: in order datagram delivery, guaranteed minimum bandwidth to flow, restrictions on changes in inter-packet spacing, and so on. So you have to choose your network service model according to this. So we said that internet uses best effort, so it doesn't guarantee delivery or minimum speed and so on. So as you can see, the answer is almost no to all of the properties. So you might think that maybe it is a bad choice, right? Why are we using this? Because there are other methods that sometimes say yes to this question. So as we can see, internet's best effort service model, no guarantees on successful datagram delivery to destination. They call that at the TCP. We have to do this reliability by ourselves, by devices checking if that packet is received and so on. Last time we talked about this. Also, no guarantees on timing or order of delivery. And also no guarantees on bandwidth available to end-to-end flow. So it is almost not everything. But there are other service models. For instance, at the ATNs, we have constant bitrate. So if you have a channel that has a constant bitrate communication, this actually provides you some, guarantees, right? So this is especially in the timing and order, but it is also provides, guarantees on reliable transfer and so on. So as you can see, there are other models here. We could choose them, but internet's best effort actually right choice. I mean, it doesn't look like this by looking at the table, but actually it works. Okay. Again, here you could use some other methods defined in RFCs, which allows you guaranteed transfer and so on. But generally, we would prefer this one. So here are the reflections on best effort service. Simplicity of mechanism has allowed internet to be widely deployed, adopted. Sufficient provisioning of bandwidth allows performance of real-time applications, for example, interactive voice video, to be good enough for most of the time. As you can see, we don't guarantee anything, but we still can have, video conferencing and so on. So this is why it somehow, works. Replicated application layer distributed services, data centers, content distribution networks connecting close to clients' networks allow services to be provided from multiple locations. So as you can see, most of the properties are done on the different layers so that we have reliable communication and so on. Congestion control of elastic services helps. It's hard to argue with success of best effort service model. So this is the idea. It really works well. So let's stop here and then talk about what is inside the router.